Well, firstly, thank you, BWCE, for inviting, obviously, Mitsubishi to present. The opportunity to promote low-carbon heating is always greatly appreciated, and I totally sit by Kate's comments. Reference fabric-first approach is always the correct thing to do. There's never a time where technology should be thrown at a project, in the wrong application, really. The presentation, basically, from this point of view, touches upon just some key areas when considering moving to an air source heat pump from a fossil fuel or direct electric system, and cover off some of the previous presenters, Kate's information, just to sort of hit home some of the points of that decarbonisation of the grid that's so important. Simon Watts, who's also here, his details at the end of this presentation, and he'll be more than happy after the event to cover off any specific details that you have at the end of the presentation. So I think it's always before going into the product benefits, which obviously there's a lot of. It's kind of worth spending a minute just on the history and the future of heating in the UK. Really, since the dawn of mankind, we have always had some basic needs. Light, fuel, food, shelter, and heat. Incredibly, we're still, looking at it, still burning fossil fuels to keep warm, which is, I think we'll look back on in sort of 20, 30 years' time and think it was a bit archaic, really. But, we've had electricity in properties since the 1930s, replacing even gas lighting within some properties. So there's still a journey to be had, but it's clear the defined future-proof economy is going to be based on electricity. 1960s really saw the rise of cheap fuel to consumers, probably without recognising necessarily that long-term impact into the environment. But as I mentioned, the government really now sees the electric economy as a long-term low-carbon strategy, make the grid cleaner, and we have an energy system that kind of improves over time as that improves. And it's a point that Kate kind of touched upon earlier, really, and it's that decarbonisation of the grid. So looking at the changes in SAC, for instance, the impact of low carbon energy generation is clear with the introduction of more wind, solar, nuclear, tidal, to name kind of a few, really, has enabled the UK to reduce the carbon output of our energy production dramatically. The carbon generated from gas and other fossil fuels basically doesn't change. So where we can actually start implementing more renewable technologies, the grid evolves and becomes and continues to get cleaner. And for every home really that we don't install low carbon technology in and install fossil fuel boilers, we increase the carbon output until, for instance, the heat pump, and it's not just all about heat pumps, is retrofitted. So it's good to see no more gas boilers in new build properties, ideally from 2025. However, that kind of needs to be implemented from our point of view sooner, so we're not kind of compounding that problem. So I know a lot of people on this call are already going to know a lot about heat pumps, so apologies for teaching people to suck eggs, really, but I think it's always worth sort of just going back to the basics. Why are heat pumps really kind of top of the government's agenda to kind of reduce carbon across the UK? And it's all about this kind of coefficients of performance and efficiency. In a way of explaining the efficiency of the system. So it's basically how much energy goes in compared to how much energy comes out. If you have a fossil fuel boiler, like a gas boiler with an efficiency of 80%, then we need to put 1 kilowatt equivalent of gas energy to deliver 0.8 kilowatts worth of heat, and therefore a COP of 0.8. As shown here, using a heat pump, we can harvest renewable energy, which increases the energy output. So for every kilowatt of electricity to run the heat pump, enables the system to collect 2.2 kilowatts worth of renewable energy to deliver a total of 3.2 kilowatts. Therefore, a COP of 3.2, or in theory, if there was such a thing, an efficiency of 320%. The seasonal COP is the efficiency, but over the whole year, which is a more realistic figure and one that the industry has adapted. What makes a successful solution? What makes for a successful technology, really? And it takes a number of different things into consideration. It needs to be economical, basically affordable to the market. Now, there's many technologies out in the marketplace, such as things we've seen in the past, like fuel cell boilers, which in the past have been relatively expensive. A great piece of technology, but it needs to be scalable. it needs to be able to be tapped into existing production lines. Now, fortunately, a lot of heat pumps come out from air conditioning based manufacturers. So it's a matter of adapting those production lines to increase and hit those economies of scale. So it impacts the first point, which is the economical factor. Then the environmental benefit, it must have an environmental benefit, as more of the same problem is kind of counterproductive, really. And then finally, for me, it's the most important part. It needs to be publicly acceptable. You know, change is difficult for many to adapt, and the easier and more manageable this is, the quicker it will happen. Now, there are various different types of heat pump. You know, I'm obviously going to be, you know, biased and talk a little bit more about air source heat pumps. But you know, you know, there's ground source heat pumps. You know, you can fit with either boreholes or slinkies to harvest the renewable heat. The advantage of a well-designed ground source heat pump is that you maintain an equivalent of, you know, 8 to 10 degrees outdoor temperature, which helps maintain the efficiencies even down to the colder external conditions. You've got exhaust air heat pumps, which kind of sit inside the property and utilise the warm air generated or the heat generated inside the property. And there's a little heat pump in top, and you've got an immersion heater just in case the heat pump isn't able to necessarily do the full job. You've got a water source heat pump, which in theory does a very similar job to the ground source, apart from you don't need the boreholes, but you just need a large body of water to be able to extract that heat from. And we've been involved in projects, for instance, using the Thames, where we've put 170 flats using the water and the heat from the Thames. You've got to be quite careful about, weirdly enough, taking all the rubbish out and putting it all back in. They don't like you sort of filtering too much out of certain bodies of water, and you need to make sure that that body of water isn't going to be frozen if everyone starts dipping into it. But essentially, they all do the right job in the right place. The worst situation is putting the wrong products is only in the wrong application. So there is no real right or wrong. It's just making sure you actually sort of consult the right person to make sure the right technology goes in the right place. So yeah, how does a heat pump work? Again, apologies for those that know this through and through and be told again and again. I'm just going to focus on, yeah, as I say, air source heat pumps. The beauty of an air source heat pump is it's a very simple piece of technology. You know, we learned very quickly that there's no point telling everyone the inside leg measurement of how a heat pump works, because everyone sort of tends to switch off. Essentially, we're just putting a boiler outside the house in its simplest way. But it's always compared to a refrigerator, and it's got the same 4 main components. So when we put our hot food or the food we want to cool down and make sure it doesn't go mouldy in the fridge, that heat is actually absorbed into the liquid refrigerant, which sits in the evaporator. Now that liquid refrigerant basically boils off, turns to a gas, and goes through the compressor. Now the compressor is like a big bicycle pump. It takes that gas and superheats it. And then when you put your hand around the back of the fridge, it expels that heat to the kitchen. So it's always hot to touch when you put your hand on the back of a refrigerator. Then you've got the expansion valve that takes that gas, takes it from a small area to a large area, so it returns back to its liquid state, and the whole process continues. Really simple, straightforward bit of science. And that's exactly what a heat pump does. But instead of your food source, your energy source coming from your food, it comes from the air that you're pulling across that evaporator. And instead of delivering that heat from the back of the fridge to your kitchen, essentially you're passing that heat to the water that's come from the house, and it gets heated up in the back of the heat pump, which is being rejected via the condenser, and then continues that process. So it's a very nice, straightforward piece of technology, very reliable. Very rarely do we ever change our fridge unless we've had more kids, dare I say it, or we've changed our kitchen. There's 2 different types of heat pump. There's splits and monoblock units. In short, monoblocks are sealed systems like your fridge. Split systems are like air conditioning systems, which require an F-gas engineer to install alongside your heating engineer, as refrigerant pipes will be needed to install to the hydro box inside. And as you can see in between the cylinder and the outdoor unit at the bottom, there's an extra box required. When the outdoor unit needs changing, you would also need a refrigeration engineer to remove the old unit and install a new one. Now, monoblock units are the preferred choice for the majority of clients and predicted to increase. And to reflect that, Mitsubishi are no longer pursuing a split unit product for this reason in the UK. Now, it's all a lot of talk at the moment about who's got the best box, the cleanest box, you know, a lot of figures being churned out, but it's all about that perfect balance, really. That box is one part of the delivery mechanism to make sure that everyone's expectations are met. It's all about making sure that design, installation, and support to the end user is delivered for that perfect balance. And to start off with, it's the design. You know, start off with fabric. And as Kate said, you know, there's no point putting a product into an incredibly leaky building, oversizing the heat pump when you can actually spend the money, making sure that you've got this nice sealed box and then put the right product in to future-proof that scenario. So heat loss is an energy loss from the interior of a dwelling to the exterior. The rate will vary at different outside ambient temperatures and be dependent on what fabric the property is constructed of. You know, the windows, the walls, the loft insulation, etc. The rule of thumb guide at the bottom gives you an indication of the heat loss based on the age of the property. The newer the property, the better the insulation, less heat is lost, and the smaller the boiler needs to be. Insulation is always the best starting point before investing into a technology. And it's ensuring, and I don't want it to become a product Mitsubishi presentation, but what we've tried to do as a manufacturer is make sure that going back to that right product for the right application is making sure that you've got a range of products to meet your demands. So installing a heat pump that's too large for a property will mean that that unit will operate intermittently rather than constantly, which is not efficient. Installing a heat pump that's too small, it's pretty obvious, will not deliver the right amount of heat when it gets cold outside. This is why choosing the right installer to carry out the right design and the right product is key to meeting everyone's expectations. Also on the right-hand side of this picture, you can see, you know, examples of the pre-plumbed cylinder. I'd like to think we kind of like a lot of talk about modular construction and houses built in factories at the moment. And we kind of put ourselves in that ilk of making sure that we can do as much in the factory environment to make sure the quality of the product before it arrives on site can be dealt with. So you're maintaining a decent, consistent outcome for everybody. So that cylinder is needed to install. So part of that design process is that you'll need to accommodate a cylinder inside the property. One area that we've clearly heat pumps were not able to, in the early days, some heat pumps weren't able to deliver the right amount of heat when it was cold outside. When it was, the capacity dropped when the temperature dropped. Now with modern day design, well-designed heat pumps, this isn't the case. So as we can see here, the 14 kilowatt Ecodan works all the way down to -15 degrees. So this gives the confidence to the homeowner that can always get the right amount of heat no matter what those outdoor conditions are. So it's peace of mind that you're designing for that right application again. This is a little bit of flexing, I suppose. You know, I can't help it within the presentation. You know, we've already looked at seasonal COP means, and this gives you a good idea of, you know, how easy it is to compare products with each other. Here we have like an example of one of ours, an 8.5 kilowatt at different flow temperatures. So you normally design a heat pump at 45-degree flow temperature, which is the middle one. Two key things to take away from this is the ERP, the energy rated product label. This is the same as the one you get on your home appliances to enable you to choose the most efficient product. As you can see here, the product's at the highest level, an A+++. So we're at the kind of highest echelon that you can actually get to. Really the next thing to focus on is the dark blue column, the dark brown column, which is the seasonal COP for the Ecodan. And this means that when designing a system at 45-degree flow temperature, we get a seasonal COP of 4.1. So that's an efficiency of 410% efficient. This not only impacts how efficient the product is, therefore reducing the running costs to the end user, but it also improves the return you get back from the RHI. So that higher the seasonal COP on the NCS website, the higher the return and the lower the running costs. So we've got a good, okay idea now with regards to the understanding of why air source heat pumps might be, hopefully, a good alternative to what fossil fuels and direct electric systems. It's important to allow for planning on projects, especially large installations. Sometimes, you know, we've done projects, South Lanarkshire, which was 1,500 units over the space of 18 months. So having to, if you had to go into planning for every single installation, that can hold up those projects quite considerably. So permitted development is a nice way of getting around this. You can install a heat pump using permitted development if the product installed fulfills the following criteria: MCS accredited. It also needs to be, which is microgeneration certification scheme. It needs to be under 42 dBA and sound power level when measured 1 meter away from the next door neighbour's habitable room, to make sure that you're not inconveniencing your next door neighbour. It needs to be under 0.6 cubic square meters to make sure you're not putting a monolith obstructing people's views, etc. So it's a keen way of measuring the size of the system. One heat pump, one property, and 1 meter away from the boundary of the property as well. And then finally, not listed on a listed building or a World Heritage site, which are kind of very few and far between, but that gives people the opportunity to not have to go through planning. I'll go through some basic install requirements to put it on the radar. It needs to sit outside. You know, I mentioned about the way the process works. So you're bringing that warm air across that evaporator to absorb that free energy, which sits all around us. As soon as you put it into a confined environment, the air that comes off the front of it is of course colder because you've taken the heat out of it. You put it in an enclosed space and suddenly you're reducing the temperature of that room, and therefore over a period of time, the amount of free energy available in the air reduces, so the performance drops. Condensate removal. You can see in this particular picture here, you can see gravel around the outside of the concrete plinth. That enables that condensate to drain away. The 8.5 kilowatt unit produces anywhere up to 2.5 litres of distilled, in theory, water potentially every hour. So you need to make sure you can accommodate that, because the last thing you want in wintertime is that water to kind of come across your patio outside your French doors and freezing. It's not the best thing. Single phase electricity supply, insulate your pipe work, you know, isolator on the electricity and pipe work, and anti-vibration blocks you can see here, and position of airflow, small space behind so you can clean the unit out and you can bring the airflow through the unit, and adequate airflow out the back, out the front, to make sure you don't have any obstructions. So all relatively straightforward stuff. Still, we see kind of simple things like the pipe work not being insulated sometimes, and it's kind of like you've made all this effort, and then you end up sort of heating the outside environment because you haven't necessarily insulated that pipe work. So some basic key areas. Inside the house, you know, we've already mentioned the cylinder space which is required, which will need to heat the pump, make the heat pump compatible, as the flow temperature from the heat pump is lower than that of the boiler. Some of the radiators might also need to be increased, and this makes the product as efficient as possible. There is a good chance some don't need changing due to the fabric of the property being improved since the radiators have been installed. This example at the bottom here, which you can see, you get the same level of heat out into the room using a lower flow temperature, taking from 65 degrees to 45 degrees. But that would mean you'd need to increase the size of the radiators by, for instance, 65%. This increase can be normally accommodated by taking a single panel radiator to a double panel radiator. So the fear of putting a 20-meter long radiator in the living room is normally kind of put to bed because the availability and the efficiency of modern day radiators. We always get asked how easy is it to service a heat pump? Really kind of straightforward, really. It's without kind of knockings. I'm sure there's installers on the call. It's a bit of a chimney sweep job, to be fair, on the outdoor unit. It's more of a visual inspection. There's not really much you can do. You need to make sure you're cleaning the debris away from the back of the unit, making sure the fan's running properly, visually check the electrical connections, pipework insulation, etc. You know, it's a lot of things that absolutely 100% need to be done on an annual basis to maintain the warranty. And then you've got the indoor cylinder unvented checks. So it's really important it's done by a professional to make sure that your performance of your product is actually continually maintained. Controls and monitoring. You know, we've spent a lot of time and money and research and development in the performance of the unit. This one controller that you're looking at now has probably saved us more visits to site than anything else. And this came from feedback sessions with a lot of social housing providers that didn't want too many features on a controller. They just literally wanted an up and down button for room temperature, a tap for hot water advance, and a bag for holiday mode. So it's a really easy, straightforward and engaging piece of equipment. to make that kind of an aspirational front end, something which is easy for the end user to adhere to. Taking that a little bit further, we've just launched literally this week a new piece of kit. Now it falls in line with criteria that the industry is kind of driving towards, which I know Alex is going to go through a bit later. But you know, things that we put in there are simple setup. So you know, it's that simple to, for the engineer to go through the commissioning settings as a step-by-step guide. The connectivity, every unit goes out the door with connectivity, so you can connect via your broadband, not only to control your heating system internally or when you leave the property, but it also gives access to the customer services to remotely diagnose fault to minimize any disruption to a homeowner. And then finally, performance. Many, you know, and from the very beginning, the monitoring of heat pumps was key to gaining people's confidence. It threw up the question of everyone wanted their system to be monitored. Everyone likes a glossy brochure, but there's always a bit of pessimism in there. How realistic is the manufacturer's data? So it's really important that every unit that goes out the door for every manufacturer to have clear visibility to the end user of how that unit's performing, and to make sure that everyone's aligned and the expectations are met. Now, I know Kate actually touched upon the RHI, so I'm not going to overly dwell on this. It's always a useful thing to have a look at your EPC when you get home, just to check to see how much you'd be eligible for. I will just quickly go through an example of how you calculate it. But you basically add your heating and hot water kilowatt hours together. For instance, in this case, 15,500 kilowatt hours. If we take a seasonal COP of a heat pump of 3.89, that means we need 3,985 kilowatt hours of electricity to produce that 15,500 kilowatt hours of heat. So we're actually harvesting 11,515 kilowatt hours of renewable heat. That's the bit we get. That's the bit the government's paying out for. You multiply that by the tariff, and that gives you £1,233 per annum. Multiply over 7 years, that's £8,633. Now, on this list here, you can probably have a look at which property on there relates to your own home. And once you've seen that, the yellow figure on the right-hand side is an estimate of what you'd actually end up getting paid out over a 7-year period. So it gives you an indication, and this is never designed for a get-rich-quick scheme. This is about supplementing the costs and capital outlay for people to enable them to make the right decision rather than just factoring back to the default of replacing what they've already got. I was asked to cover the estimated air source heat pump installation costs. This is always a sensitive issue because it varies, you know, and all I will say is, you know, the cost of an electric Mitsubishi electric package, Ecodan outdoor unit, pre-plumbed cylinder controls start at the smaller capacities at around 4,000. They go all the way up to sort of 7,000. On top of that, you need to include the installation from an NCS accredited contractor, and you need to include the components I've added here as the bullet points over and above what would be supplied by Mitsubishi Electric. And it's best to make sure that you get, and I think Kate mentioned it earlier, that actually it's a false sense of economy sometimes to go for the cheapest quote. It's always making sure you're getting a quote from a reputable contractor that has the right credentials. And then estimated air source heat pump run cost. Now this is kind of like a broad overview really, to give you a genuine comparison of the type of technologies that you might be replacing. Now we've been relatively kind on the electric storage radiator, which we've placed at 7p, which would normally be people's off-peak tariff on economy 7. But you can see if you were to be on a 12.5p kilowatt hour tariff for electricity and a pessimistic efficiency for a heat pump of 3, you'd be delivering for every useful kilowatt hour about 4.17p pence per kilowatt hour, which is roughly, ballpark, I know this is kind of drawing it in line with gas. Gas is cheaper, of course, but the system efficiency is normally realistically of a boiler around just over 80%, which gives you roughly the same running costs as an air source heat pump for a gas boiler. It's the off-gas grid properties that have always been a key focus for us, which are oil, LPG, and electric storage, where you would be looking at a relative saving anywhere between 35 and 50% saving, depending on how much people have used in the past. The one caveat to that, I would say, is properties that we install and replace electric storage radiators, very rarely do people end up heating their entire house off electric storage radiators. They normally have the one in the lounge and the one in the bedroom, and they'll kind of run in between them both because the rest of the house is an extravagance to heat. So, using an air source heat pump, we say you're improving the environment of the property as the key point, and the relative saving will obviously follow. So from the final slide, from my point of view, and it's a bit of a whistle-stop tour really, but it's really kind of time for change. The government predicts, the Heat Pump Association predicts, 1 million heat pumps will be installed every year from 2025 onwards. So it's not kind of it's not sort of something which is kind of here today, gone tomorrow. And George Clark is our ambassador, and he's fully embedded in making sure that, and it's an important part for us to bridge that gap. And it's that gap that we feel we've got the products, we've got a delivery mechanism to be able to take it to marketplace. And with legislation and organisations like Kate's, we feel like we're well primed really to take the production facilities and match the requirements of the marketplace with that continued growth and appetite for reducing carbon within the UK to meet that government target of 80% by 2050. So from my point of view, that's the end of my presentation. So I appreciate that, Peter. That's very kind of you to invite us along.